Hello everyone, my name is Kevin Lin, and in this video, I will demonstrate my 49Y final project video. The purpose of this project is to create a 3D scan of an object on the UMD campus using a custom-built low-cost LiDAR sensor. This project will help us get to know the fundamental principle of LiDAR sensor and provide us with some hands-on experience in remote sensing. My target of choice is a Tau Beta Pi band located in front of Martin Hall. I chose this object because I'm a Tau Beta Pi member and one of our initiation requirements was to create a custom band. I thought it'd be cool to 3D print my custom band from the 3D point cloud that I was able to generate from a LiDAR scan. So what is remote sensing? Remote sensing is the science of obtaining information about an object or area from a distance. There is passive remote sensing, such as the RGB camera, which does not transmit any photon. It only receives light or photons coming into the receiver. Or an active sensor, such as LiDAR and radar, they create their own electromagnetic energy that's transmitted from the sensor toward the terrain, interact with the terrain, producing a backscatter of energy that is recorded by the remote sensor's receiver. So my LiDAR sensor includes a 3D printed LiDAR mount that's in two-part pieces provided by Dr. Mitchell. And on the mount, there is a 5-volt line laser that acts like a transmitter. It's powered by the Arduino, and the Arduino is in turn powered by a 10,000 milliamp power bank. The receiver is the Raspberry Pi camera that's connected to the Raspberry Pi and is also powered by the 10,000 milliamp power bank. And the chassis is mounted on a tripod mount with a cell phone. In the field testing, we use a cell phone to record the angle of elevation at which our laser is pointed at, so that we can combine different angles into translate into a mesh cloud to produce a 3D point cloud. So our LiDAR sensor used the LiDAR triangulation formula to calculate the distance from the sensor to the target. The farther the distance is, the closer the laser pointer appears to the center line. So in here, the laser is 5 feet away, and in here, the laser is 2 feet away. So at farther distance, the line laser appears to be closer to the center axis. And since the separation distance between the light emitter, the line laser, and the Raspberry Pi camera, the lens, is fixed at 12 inches, we can use the formula to calculate the distance from the sensor to the target. As the distance increases, the scatter angle between them will decrease. So to calibrate our sensor, the line laser image was taken with object 0 to 10 feet away from the sensor at 6 inches increment to calibrate the sensor. After each image is taken, then we use the color picker to pick a HSV value that finds the red line laser on the image, and then we was able to plot so this image shows a point laser, and this is a line laser. Was able to plot the pixel from the center of each one of the laser data along with the distance from the target. Those are manually input into the data for calibration purposes. And the experimental curve is our laser data, and the theoretical curve is using the triangulation formula to derive. And we see that this two line matches pretty well. Another step before we do the field testing is to make sure the line laser is aligned parallel to the center axis to make sure that each scan is distinguished from each other and there's no weird overlap if the laser was not parallel and able to flop around. Next, this is a video of my data collection process. I scanned 4 sides of the Tau Beta Pi band. One image for each angle of elevation, so there's about 42 images per side, and I used about 10-second exposure for most of the image, except on the left side I used shorter exposure because there's a lamp on this corner that was messed with the how bright the red laser is. I try to keep the LiDAR instrument at the same distance elevation from the target. It's not quite identical for all four sides, but I try to keep them at about the same elevation to eliminate the difference between the curvature of scanning. So the LiDAR lasers scan at this area. When they scan this, the point directly across from the sensor will appear to be farther away from the sensor versus the point that's lower in the target that will appear to be slightly closer because there's a contour. So I try to keep the line laser at the same distance such that the contour on all four sides is the same. And later on in MATLAB, I can apply a fix on the same height to solve all four of the sides altogether. And I choose to scan to do the field scan really late at night to eliminate some of the passengers and also cars driving by when I scan the backside to eliminate some of the unwanted bright lights in the background. So after I gather all the image from each side of the data, I apply the same HSC format to find the red line laser that I was able to get for each image. I use about 2 HSC value, one for the concrete base, one for the actual tau beta pi band for each side of the image. And after all the HSC values is found, I use the data generation file to generate a text file that contains all the point cloud for each side of the image. Then I was able to import all 4 of the text file into MATLAB to combine them. There's 4 primary techniques that I use to simplify or eliminate some of the noise. First, a lot of data is coming from the background, such that the laser light is not hitting on the actual target but hitting like a tree in the background. So I delete a lot of data from outside of my target. And to stitch the image together, I use the concrete base as a guide. So I align the edge of the concrete base on all 4 sides together to make sure I have a sharp connection between the front and the right side. So I was able to do that by flipping the X and Y axis on the left and right side of the image to rotate them 90 degrees. And on the back side, I was able to flip the image backward and then transpose them for a set amount of distance to make the backside facing inward, as similar to the same side. And then after that, I was able to concatenate all 4 sides of the data cloud into a single data cloud that I was able to further eliminate some of the noise. Here is my unfiltered data. You can see there's a lot of noise from the left and right, and the transpose is not quite complete. So the backs look really narrow compared to how wide it is. And here is my filter data. You can see all these edges is aligned pretty nicely. So after I generate a single MATLAB result file, I was able to import them into MATLAB. I used the number sum of 1 to make sure all the vector is pointed at the same direction. Put some surface reconstruction depth of 15, number of sample of 5 to smooth out all the surface. And then I was able to achieve this MATLAB. We can see our 3D plane cloud that our width is slightly over 20 inches. Our length is also slightly over 20 inches, and our height is about 55-ish, so slightly shorter in height, but the width and length of our 3D scan is similar to that of the actual target.